Hello, everybody. Welcome to a quick segment in 6838. Normally in my office hours, I would go through some extra calculations with you all to get some extra practice, but of course we can't really do that in our online setting, so I thought I'd share this short video to get a little bit extra practice taking first variations, just like we did in Lecture 2, and also to motivate one more formula for the curvature of a curve, either in R2 or R3. So here's going to be our basic setup. We're going to think of arc length as kind of like a function from curves into real numbers. So here's our curve. We'll call our curve gamma of s, and we're going to assume that our curve gamma of s is parameterized by arc length, or PBAL in our terminology. So the basic thing that we can do is we can think of arc length as some functional that takes in a curve gamma of s and outputs its length. Now, our question here is we want to be able to prove useful theorems like the shortest curve between 2 points is a straight line. So that might benefit from help by essentially taking some notion of the derivative of the arc length functional. So remember that the arc length of gamma is given by a relatively simple expression. The L of gamma looks like the integral from a to b, assuming that this is gamma of a and this is gamma of b, of the norm of gamma prime of t dt. Our curve is parameterized by arc length, then we can actually just substitute a 1 here, right? The length of the curve is just b minus a. But I'm going to leave it like this because we're going to take the first variation, and then our curve is no longer going to be parameterized by arc length. So what do I mean by that? Well, in addition to having a curve gamma, now I'm going to assume that we additionally have a second function, v of t. And I'm not going to be able to say a whole lot about v of t. I'm going to say that we're going to take a v of t, which maps the same interval from a to b into, let's just work on the plane, R2. You can put a 3 there and it really wouldn't make a difference. And we're going to make one additional assumption on v of t, which is that v of a equals v of b equals 0. Okay, so what's the picture so far? I'm going to think of v of t like a vector field along my curve, like little hairs that I could attach, right? So we know that it's 0 on the 2 endpoints, but other than that, maybe our field points, like that for a little while, maybe it points up, and then it goes back to 0 on the other end. So this is like v of t. Now, what we're going to do, essentially our goal here is to come up with some notion of the derivative of arc length in the v of t direction. Now, this is kind of a complicated thing, right? Arc length is a functional that goes from curves into their lengths, and I'm trying to differentiate it. So what that means is that if I take a tiny perturbation of my curve, I want to know how arc length will change in response to that perturbation. So in our notation from 2 lectures ago, what we're after is the following. What we want is to compute the first variation, or the Gateau derivative of arc length, centered at the curve gamma in the v direction. Now, there are many different ways to motivate how we might compute this formula. I'm going to try and do it in a way that doesn't require quite as much notation as we did in Lecture 2. In particular, what I'm going to do is I'm going to look at a sequence of curves that we're going to call gamma sub r. So we're going to define gamma sub r of just some general parameter t. I'm no longer going to put s here because it's not arc length necessarily. And it's going to look like the following sum. It'll look like gamma of t plus r times v of t. So geometrically, let's make sure that we understand what the picture looks like so far. So remember that our curve is gamma of t. That's what's shown on the slide here. And then we have these little hairs sticking off of the side of our curve, which are vectors. So now we've defined a new curve, gamma r of t, which is like a little displacement of gamma in the v direction, right? And the amount that I displace is equal to r. So notice that like when r equals 0, I've just recovered my original curve, gamma 0 of t. And then as r increases, I take my curve and I displace it along v more and more and more. So one thing that I can do is I can look at arc length as a function of r, which is to say that as I displace my curve away from gamma, I could ask the question of how arc length changes. And that leads me to a function that I can call L of r, which is just going to be the integral from a to b of the norm of gamma r prime of t dt. Okay, so incidentally, when I use prime in today's little discussion, I mean differentiation with respect to t, not with respect to r. Hopefully I'll be consistent about that in the remainder of our discussion. Okay, so there's our expression, and now essentially what we want to do is take the derivative of L of r. In fact, one thing that we can convince ourselves quite easily if you return to the definition of the Gâteau derivative is that computing dl centered at gamma in the v direction, that's a gamma, is exactly equal to L prime of 0. This just follows directly from the definition of the Gâteau derivative. So let's actually go ahead and compute gamma prime as a function of r. Or sorry, what did I just say? L prime as a function of r. So if we just differentiate under the integral, what are we going to get? We'll get the following. We'll say L prime of r equals, well, it's d over dr of the integral from a to b of the norm of gamma r prime, like that. Okay. Now, here's something that you may or may not remember from your calculus class. It's called differentiation under the integral sign. And here's the basic point. My integral is over a variable t, and my derivative is over a variable r. And r is sort of a parameter of the expression inside of the integral. So in this case, the integral is basically just a glorified sum over different t values. Right? And just the same as we can exchange derivatives and sums, we can also exchange derivatives and integrals. So let's do that. Essentially, what I'm saying is that this is the same as the integral from a to b of d over dr of this norm, gamma r prime of t, integrated over t. Okay. So now we're in pretty good shape. So now we're going to make use of one small formula that I want you to prove at home, which is as follows. I've got it in my notes here to make sure that I get it right. That in general, if I have some vector w of t, then I can differentiate its norm as follows. I can write d over dt of the norm of w of t, this is just a generic formula, is equal to w dot product w prime divided by the norm of w. This is just a useful identity to know, and you should prove it at home. This is just a vector calculus kind of an exercise. Okay, so let's apply that here, but here we're differentiating with respect to r and not t. Yeah? So what are we going to get? We're going to get the following. Well, it's still the integral from a to b. Well, now we have w dot w prime. So in this case, it's gamma sub r prime. This is a little confusing, I admit, because the prime here is with respect to t, but here I'm differentiating with respect to r. So I'm sorry, I should have put an r in the expression here, but it's too late. Right, so we're going to substitute in our vector first. So this is going to be gamma of t plus rv of t, like that. Dot product with the derivative, right? That's this w prime. So in this case, this is with respect to r. Notice that the derivative with respect to r here is just v of t. All of that divided by the norm of our vector. So that in this case is again just gamma of t plus rv of t. like that. Okay, hopefully I haven't totally confused you by talking in circles. So now, one thing that we can do is substitute in r equals 0, because at the end of the day, that is what we're trying to derive. So what happens in that case? Well, let's go ahead and write it out. So, in other words, we want L prime of 0. And that is going to be equal to, well, this term vanishes, so I have gamma, oops, I've made a bit of a mistake because there's a prime here. Okay. So, when I substitute in r equals 0, I'm going to have gamma prime dot v prime. So this is the integral from a to b of gamma prime of t dot v prime of t. All that divided by the norm of gamma prime of t. Okay. So, hopefully that makes some sense. And now when we step back and look at our expression, we can start to do some simplification. Now in particular, notice that we have gamma prime divided by the norm of gamma prime. Well, that's exactly the unit tangent to our curve. So this is the integral from a to b of the unit tangent, b prime of t, dt. Okay. So now we're going to do one more trick, which is that we're going to integrate by parts. Notice that we have a function of t times the derivative of another function of t, right? So integration by parts is going to be boundary term minus another term where you put the derivative on the first thing. So in other words, let's see here. Well, we have the boundary term, which is going to look like t dot v, evaluated at a and b, minus the integral from a to b of the derivative of the unit tangent with respect to t. Remember that our curve is parameterized by arc length, so that's just the curvature times the normal dot product v, like that. At this point, the t I could probably write as an s. Now remember that we made an assumption all the way back here that v of a and v of b are 0. So what are we left with? Well, we're left with the integral from a to b of kappa of t n of t dot v of t dt at the minus. Okay, so this was the formula that I wanted to derive in our short segment here. Again, remember what it's saying. It's saying that if I take my curve gamma and I start varying it by moving points along the vector field v, then I can ask how the arc length of the curve changes in response to that little perturbation. And what we just proved is that the amount that arc length changes, at least right at time 0, so just as I start at my curve and push a tiny, tiny bit among v, is that I get a rate of change of arc length following this expression. So, one way I can understand this is that it's sort of like the inner product between this function kappa n and this field v. I can kind of, in quotation marks, write that this is some inner product between v and minus kappa n. Now, remember before when we talked about the when we took differentials of functions that were finite dimensional, we had a formula that looks kind of like this, right? We had df at x naught in some v direction is just equal to v dot the gradient of f at x naught. So if you kind of step back and look at this formula here, what it's telling us is that the differential in the v direction, like the directional derivative, is nothing more than the dot product between the direction where you're computing the directional derivative and the gradient of your function. We'll take a look at what we just showed in this expression here. So here, we took the first variation of arc length of our curve. What we ended up with was the inner product between the variation direction and minus kappa n. So remember in gradient descent algorithm, like if we want to decrease a function, the way that we can do that is we can flow our point along the gradient, or really minus the gradient in the gradient descent algorithm. So here, minus the gradient is the curvature-weighted normal of our curve. So what is that telling us? So let's say that I have a curve gamma. Well, then the curvature-weighted normal is going to be the direction that I can flow the curve in order to decrease its arc length. So it's going to look something like this. You can see that these arrows I'm drawing, other than being quite imprecise, are basically pointing in the direction where eventually my curve is going to converge to a straight line. And so if you want to read about flowing a curve along its curvature normal to decrease its arc length, this is a name. This is curve shortening flow. And this technique and sort of variations of it are used to beautify curves in computer graphics and approach other problems in other domains. So what was our point here? Essentially, to summarize, since I know I stumbled through it a tiny bit, we started with a curve, and in addition to that curve, a vector field that left the endpoints of the curve alone, but otherwise was a way to kind of vary the curve in some direction. And then we asked the question of, can we figure out the rate of change of arc length of the curve if we perturb it in the v direction? The way that we did that is we cooked up a sequence of curves that at r equals 0 agrees with our original data and then moves in the v direction, and then differentiated arc length as a function of r. So when we did that, what we ended up with, after we moved through this entire derivation here, was this derivative formula on the right-hand side, which is a pretty handy one. And in particular, if we compare it to our expression for the differential, what we see is that flowing a curve along its curvature-weighted normal is some local way to do gradient descent on arc length and decrease the length of the curve. So this gives us yet another interpretation of curvature. It's kind of like the norm of the rate of change of arc length as a local function along our curve, or rather the norm of the amount that we can decrease arc length by making small perturbations in our curve. Notice that kind of agrees. Like if our curve is a straight line, the curvature k here is equal to 0, which makes sense because there's no direction we can move our curve to make it any shorter. This also is going to motivate another discrete definition of curvature that you can derive on your homework, where now your curve is a sequence of line segments. And you differentiate the length of this polyline as a function of the positions of the vertices, and we'll see that you get a very similar formula. So in any event, this is just a little extra segment to motivate yet another computation that we could do that, after we do a lot of calculus, ends up at a very familiar formula, which is the curvature of a curve. So with that, I'll still see you in our next lecture.